So good morning, everybody. When Manuel Blanco asked me to come here and speak, I thought I'd thank him. I thought, as usual, that I would speak science, but then I read the title, Comfort, the role of CSP, and since we are doing exercise on energy policy for Portugal, I thought it might be interesting to really show you what the role of CSP can be. And now I benefit from the fact that we had the talk of Luis Crespo yesterday, and that you understand, and I don't need to go through much detail, some of the background for what I'm going to talk about. So already, summary of my talk show to you that we already have more than 50% renewable electricity in Portugal. I'm going to tell you that we could think of a scenario for 2030, at least of 90% renewable electricity, so going from 50 to 90, and beyond 100% or almost in the future. But then I cannot resist telling you a little bit about present-day CSP research in Portugal. Of course, comments and discussions in the end. So look at the present situation of renewables, of installed capacity for hydro. The dark blue is for hydro, and light blue is for wind. Or is it the other way around? Yeah, it's okay. A little bit solar already and biomass. That's the present situation. And the installed capacity has been growing in the past. Now, the specific numbers are the following. Hydro is about 7 gigawatts, wind a little bit above 5, solar 500, so a tenth, biomass and residues 384. But then the balance is gas, about 3.8 gigawatts, coal, and cogeneration. And that makes a total of 20 gigawatts of installed capacity. Now, the interesting thing, and that's really a driver for what I'm going to say, is that we have 2 coal plants, and they are a few years away from ending their life as coal plants. So it means that very soon, in this horizon of 10 years, coal has to go, and goes with no pain. It's the end of the lifetime of coal. But coal is contributing today around 27% in energy terms. So another interesting point before we move on is something that people have talked about here. It's the fact that the different renewables are present in different availabilities in different areas. So in the north, more hydro, a little bit of hydro also in the middle of the southern part. But then wind is predominant in the center. Solar, of course, the availability, the use today is low, but the sunny part of the country is the lower south. So the renewables are distributed, geographically distributed, and that helps in terms of contribution and reliability. Another interesting point is this thing about curtailment. We still have only 60% or up to 60% average contribution, but you see that in the last years, the black line is what we needed, and this is excess energy. So there are days where the country is completely dependent only on renewables, and it may exceed the load, and then we have to export or simply curtail. The other interesting point is also that this dependency on hydro, but look at this year here, is much more than the last year. So hydro depends on whether we have rain or not. So in numbers again, 2016, we had a 30% contribution from hydro, but in 2017, only 11%. So it's a dry year and a rainy year. Wind stays more or less the same. So what does compensate for hydro? Well, that's gas here. When we have lots of hydro, we have less use of gas and coal. When that's not the case, then we have to increase gas and coal contribution. The rest pretty much stays the same. Okay, so let's go to the exercise of moving to the future, to the next decade. So as I showed to you, we have between 10 and 30% from hydro, wind about 25%, around 1 or 2% from solar today. Biomass and residues are burned and used. Cogeneration, natural gas make the balance here for between 20 and 30%, and coal to around 25%. So moving to the next decade. By the way, I want to say it's obvious, but maybe I should repeat this. I am not the minister for energy in Portugal. Okay, I'm not. I guarantee. No, not even. No, so I'm not. So what I'm going to say is not a government policy, is at best a study for a government policy, okay? It's to show it is possible. It's to show that we can have a role for CSP. So a balanced thing, and when I say balanced, it results from the numbers I just showed to you, but also from the first studies that we have done, would be to call this out, okay? So we really want to put there 0, and we will. So now we have to distribute the rest through the different possibilities. So what we have is hydro can still grow, and there is this variation between dry years and rainy years, and wind can still grow a little bit, especially if we think of offshore wind. But then there is this very important combination. Let me stress this, because this is storage. This is energy storage. It's reverse pumping, and this is being done already. If you look here at the installed capacity for reverse pumping, we now have 2,600 megawatts of reverse pumping working. And with the next hydro power plant, it's being constructed. It should start in 2022 producing energy. We will have 3,500 reverse pumping capacity, and that goes very well. That in essence, that combines very well wind and hydro. It can also use electricity produced especially by PV from solar. So, and this is an important asset of the country. Okay. Now, solar. I'm saying, okay, we can go from 1% to 30%, but how? I should explain this now. And so this is what I'm going to talk about a little bit. Solar and storage of energy to produce 30%. Let me just remind you also that we are replacing coal, and coal was in the base of our production diagram. So that's not an easy thing to do, to replace, to really compensate for this absolute absence from the base of the diagram in the future. So how are we going to do solar? Well, first of all, we will have PV, that's for sure. In particular, decentralized production, so rooftop PV, and it will come with some storage. As I commented yesterday very briefly, we as consumers in our homes, we are ready to buy a battery, even if it costs a little bit. And then we will have electric vehicles, and we want to charge them, but these guys have batteries in them. So this is also part of the game. In fact, the numbers I'm going to present are for present day consumption. The tendency in the future is for electricity to increase, to raise its share, not just because it goes, we will have a use of electricity, strong use of electricity in transport, but also because we will tend to use more electricity in buildings, as Chuck was explaining to us yesterday. It's very important. And the electricity is going to play a role. PV, for instance, combined with very cheap and efficient heat pumps, can do a very good job at heating and cooling a building. So yes, we will have decentralized production, but also decentralized production includes production for industry, includes larger systems than rooftop ones, but systems for the domestic ones, but systems for electricity for industry. And then we will have, of course, STE with its centralized production. Size matters here, with the lower cost thermal energy storage to ensure dispatchability. Now, this is a very virtuous combination, I think, and I think everybody in this room agrees. This is the old duck, I mean, this duck is about to die. We have showed him so often now that it's dead now. But yeah, so the virtuous part of this is that, of course, PV and solar go very well in this time of the day. But then we have this famous ramping up needs and sustaining the electricity supply in the evening. And CSP can do that very nicely. And I don't need to explain to you this at this point. So, but let me say something about batteries. We have been, well, we also do research on batteries. We work on flow batteries and advanced lithium-ion batteries. So we have been following this thing of batteries. And what I'm going to show you in figures is the best we know. Today, you can actually get euro per kilowatt hour from 300 to 600. I mean, the most common ones are, or commercial on the market, and better reliable ones are still on the 450, 500 range. But you could go, if you really looked, and if you're not afraid about reliability, you could get batteries like that. But what's going to happen in the future? Well, soon, and soon is what, 2-3 years, we don't know. These figures could be as low as 150 to 200 euros per kilowatt hour. People talk about an asymptote at 100 euros per kilowatt hour. With present day technologies. Let me say it again, with present day technologies, because someone might come up with an absolutely new idea, and then the story could be quite different. But then we have this question about duration. This must be put into long-term calculations. What is it, 10 years, a little less, a little bit more? 10 years seems to be a figure that everybody talks about. And we have also to consider, when we think long-term and costs, we have to think about disposal costs and the very important topic of recycling. So batteries have many technological problems associated, which are not just this cost, are other considerations that must be brought into the picture. Well, as heat, today we are somewhere between 30 and 50 euros per kilowatt hour electric. In 2 or 3 years, can we bring this cost down? There are many research groups around the world trying to do this, ourselves included, other salts, so different mixtures, combinations of salts and solids, many possibilities to really bring this cost down. This is by no means an established technology. And the duration, well, 20 years seems to be a figure that we are considering. But still, we need to, this is a question mark. This is not, I'm not stating that it lasts 20 years. I'm saying, yeah, it's likely, but there are many problems associated with salts, namely corrosion, and we need to tackle that issue. So there seems to be, present day, a factor between 10 and 20 in cost between thermal and batteries, but this difference might remain in the future. Even if this comes down as well. Perhaps we will be 10 times cheaper for a long time. I don't know. Those are the figures, by the way, that I know, the best figures that I know. So let's go back to Portugal. So what can we do? There are 3.8 million houses in Portugal. So we are considering 1,500 megawatts a peak of decentralized PV. If we just used rooftops, this will mean using 40% of the roofs. And I'm making calculations with 1,500 kilowatt hours per year and per kilowatt peak. And I'm considering now 4,000 megawatt peak in centralized during the 8 hours of the day with centralized PV. And these calculations are being made with 1,750 kilowatt hours per year per kilowatt peak. As Luis commented, well, this is using the sunny south with more sun, and PV, centralized PV tends to be done in a much more efficient way. And so, yeah, the figures are logically different. And now I'm saying, okay, we will do 4,000 megawatt peak of STE. These plants will have up to 8 hours of nominal power. These plants, by the way, produce more than 4 hours a day on average of this power. It gives you an idea. But in a good sunny day, they can store 8 hours. But then come many interesting engineering problems. Several plants can be seen as providing much more storage during the day. They just do not supply energy for a long amount of hours. So you can, 8 hours can be 16 hours or more. And also, it means keeping heat in store for 2 or 3 days. So the flexibility of having a fleet of, say, 100 plants of 50 megawatts or 40 plants of 100 megawatts is to now manage the available energy in a really controlled way. And of course, once we have storage charged, we can be very much confident about having it available for dispatch when dispatch wants. So, well, now you could ask me, but why 4,000, 4,000? Well, that's more or less the choice that Luis made for Spain, half-half. But perhaps, I mean, we have done balances of 6,000 here and 3,000 there. I think it works even better when we combine everything with the other resources. I've not attempted of doing any economic optimization. So the balance between this and that could come from an economic balance. My feeling is that the impact on costs is not, let me say it again, going 6,000 here and 3,000 there, or vice versa, has very little impact on costs. So we may choose for other reasons, for safety, for other strategies, for the way to use wind and hydro, trying to store more water, for instance, in dry years. The other reasons that would perhaps lead us towards a higher contribution of CSP. But I've not attempted this. And in any case, we should get the same figures that Luis presented for Spain. That's exactly the same thing. So I said I did not resist also talking a little bit about science. So what are we doing? So in terms of research, by the way, there is no, there are some big plants of photovoltaics in Portugal already. There is no CSP in Portugal already, but there is research. And what are we doing? So we are trying to get to new solutions, get closer to the market, and major efforts are on linear concentration, 2D concentrating solutions to operate at 560 degrees Celsius with salts. So we are looking at advanced parabolic troughs concepts and advanced Fresnel. In particular, in advanced Fresnel concepts, using the proper non-imaging optics configurations, we think there is a very good chance in the future for advanced LFR technologies. But my talk is not about that. I'm very sorry, but it is not about that. But I thought I would show you something, but let's first mention other stuff. So we are looking at also the storage problem itself, different salts, different ways of storing the energy in 2 tanks or in 1 tank, combinations of salts and solids. So these are topics that we are looking at on a large scale, as you will see. But we also looking at new solutions, new proposals for 3D concentration at the level of the receiver, at the level of the tower, configurations of the small towers, for instance, rather than big towers. And this is very important. What can we do above 600 degrees Celsius? Because 560 is just below 600, and that's the limit for the more conventional stuff that we know today. If we want to move to higher temperatures for higher efficiencies or other applications, as we will hear today, then we need to go above 600, and this is a completely different game that we are just about starting to play. So let me just show you the advanced Fresnel. Advanced Fresnel is the idea of having a much higher concentration. In our case, we are looking at multiple receiver concepts. You have here a configuration of a Fresnel second stage with a proper non-imaging optics, very efficient, but with 2 tubes. It looks funny, but it is very good, I tell you, in terms of efficiency. So it's interesting that at the level of the plant, this will also bring substantial differences. You could have a strategy in which you would use one tube to go and the other two to come back. So you would reduce enormously the piping and the complexities of connecting all of these things. You would have essentially very large collector rows, and these very large collector rows will substantially reduce the amount of piping, the amount of receivers and so forth. And so we think that non-imaging optics will allow us to develop new collectors that can be very cheap. And so this, we think that we have a really fair shot at low-cost dispatchable electricity with these new ideas. The high concentration enhances efficiency. So the overall conversion efficiencies that we are planning for the south of the Iberian Peninsula, Portugal and Spain, are 15% or even above. And this is really the figure that today we have for parabolic trough technology. In the past, conversion efficiency for Fresnel solutions was more like 8 or 9%. And this is a jump, a significant jump. It's not just a little bit better, it's 30 or 40% better. And since Fresnel is inherently cheap in terms of fabrication, we think we really have a fair shot here to low-cost production. But many other advantages. The fact that we have a much reduced number of rows means that we have less receiver length, less tubes. So we're going towards cheaper systems. The number of components, bands, pipes, valves is also reduced. The fluid volume is also reduced. Parasitic power consumption is also reduced. And something very interesting with Fresnel, it's a fixed receiver solution, and that substantially facilitates many of the engineering aspects associated with operation and maintenance on the parabolic trough collectors. So there are many other possible configurations except beyond the ones that the one that I just showed you. We can in the future make this proposal progress in terms of performance, but then we need to produce first, to demonstrate first that what we are proposing is correct. So what are we going to do about that? If this moves, yes. All right, so this is our facility. We now have an advanced parabolic trough. It's a larger parabolic trough by CSP4Climate2018, or let me put the guys there to give, why isn't it moving? All right, okay. So, we want to operate up to 560 degrees Celsius. This is the 2-tank storage, cold tank, hot tank. The technology for the parabolic trough is coming from CSP4Climate2018. It's about a 7-meter trough. The lines are 380 meters long, 2 lines. When we connect the salt loop, we'll have pipes going this way and back. But then we want to put there on the side. Oops, why is it moving? No, I don't want to go that fast. I just want to. I don't know. Well, for some reason I cannot get the Fresnel. So the idea is to put a linear Fresnel here and test of this advanced concept and test the two things at the same time on the same loop, so that we can really compare advantages and disadvantages of both technologies. The thermocline is already, has been designed already. It will go here, and so we can test also compare 2 tanks with 1 tank. We are doing research on different salts, as I said, combinations of. So I don't know why the slide is not coming. We also have a platform in which we can test concentrator modules. This platform is associated with a loop, heating oil to 400 degrees Celsius, but at up to 400 degrees Celsius, we can characterize collectors both in terms of optics and thermal performance. So in conclusion, the CSP role, the technology exists today and is ready for the transition. Even though we are looking at improvements, making things better, that's a disease that attacks scientists and researchers. We always want to make things better. But what we have today and on the market is plenty to do this transition to renewable electricity. The question is that people ask is, will this transition the transition to a predominantly renewable energy electricity production be an economic burden? I want to say, and end my presentation, to say that it is not. Perhaps it seems that it's going to be very expensive and bad because of that, but there are so many positive impacts associated with this transition that I think that from an economical point of view, it will not be a burden, a severe burden. First of all, we will reduce fossil fuel imports, and in a country like mine, where we import everything, also coal, gas, and oil, this is going to be very good. We will have the participation of the local industry, and new services and new industry will appear, creating jobs in engineering, manufacturing, operation and maintenance, installation of these things. So the job creation is a clear, positive, very positive impact. We will also do this. We will create opportunities for exporting technology and exporting equipment in the future. And then we will be, and this is not a minor point, we will already directly combating climate change, the mitigation of impacts. And this is very important, two words, and the associated costs with mitigation of impacts. These are becoming higher and higher. And when we factor in everything, I think we can clearly understand that we are in the good path. So thank you very much for your attention.
Well, that's a very interesting linear Fresnel design. I like that.
Yes.
My question, though, is you mentioned potential to lower thermal storage costs, and I'm wondering what do you see as the paths for lowering those costs?
Well, let me tell you what the kinds of things that we are trying to do, because those are basically what people try. So looking at new other salts. Trying to see how they test them, see how they behave. The idea for new salts was also associated with the idea of trying to reduce the fusion point, so that we can, the binary mixture, the classical binary mixture, has a fusion point around 220 Celsius. So we try to operate above 270 to leave a margin of 50 degrees there, and not to be close enough to the fusion point, because you don't want the salt to solidify anywhere in there. But there are other mixtures, ternary mixtures and quaternary mixtures, that can have the fusion point much lower, around 100, for instance, with quaternary mixtures, with calcium salts, with lithium salts. So the idea is to look at them because of that, but then to look at them also because of costs, and see where we could go. The other idea is to combine salts and solids. When you are storing energy inside these big tanks, you could have solids there. The salts will just flow around the solids. Yeah. And there we are looking at stones, just very basic rocks, but also at the possibility of using wastes, mineral wastes from mines, for instance, slag from mines. Some of these metal mines that we have in Portugal, for instance, are copper mines, iron mines. The slag is still rich with metals. And so it has a high thermal conductivity. And that's nice because you want to charge and discharge. So the idea is to produce some bricks with cement and these slags, and then put this as if they were rocks inside the storage tank. So that's one potential cost-lowering idea. Of course, you have to research quite a bit, investigate quite a bit the compatibility of the salts with the cement and with the slags. Yeah, this is not an obvious thing. It's not just, oh, let's do it. Okay, try it. So these are ideas. The other idea that we had, and perhaps not such a good idea, we are finding this out, was the possibility of building the storage. I mean, these storage tanks are very large. We are talking about things with 14 or 15 meters diameter, very large, 4 or 5 meters tall or more. Could we build them with cement? Could we develop a cement that would take high temperatures and be a much cheaper building? Because you need several properties for the cement. You need structural properties to hold the thing as it should be held, but cement that can take temperature and the corrosion properties of the salt. Cement that could insulate. So we set out to develop different types of cement to do this. We are in the middle in the process of doing that, but it seems like we are not being very successful with a high temperature cement because of corrosion, not because of the temperature impact, direct temperature impact on the cement, but because of corrosion. So, but if we could resolve that problem, then you would have a cheaper way to build these very large tanks. So I don't know if I answered your question, but these are ideas that go into the direction of lowering costs for storage.
No, those are good suggestions. And I guess if you look at cements, of course, you'd want to look at some of the lower carbon cement options.
Yes, okay,
because
yeah.
obviously cement is a big carbon emitter.
Carbon, yes.
Yeah.
So you're resolving the problem on one side and creating the problem on the other. No, but this gives you an idea that there are many different ways that you can follow to think about reducing costs in these kinds of things. That's all. Yeah.
Thank you, Manuel. Thank you.